Okay, so for this problem, first of all, we should know what kind of information is given. Okay, so based on the problem statement, okay, we know that the special gravity, box special gravity of the aggregate is 2.6, okay, which is let me see, which is this value, okay, and also we know the binder content, okay, the binder content is equal to 6.5, okay, which is this value, okay. Also the binder's special gravity, okay, it's 1.03, okay, so this is the binder special gravity, okay. And also we have the GMB, which is the bulk density. So bulk density of the mixture is 2.322, okay. So these are all the information we are given, okay, we are provided, okay. And then we can further, okay, calculate, okay, those important parameters for Marshall mixture design, okay. So first of all, it asks us to calculate the percentage of L voids, okay. To calculate the percentage of L void, if you check the equation, okay, we know that, okay, it can be calculated by the theoretical maximum density and the bulk density, okay. And now we already know its bulk density, but we do not know its theoretical maximum density. So first of all, we need to calculate, okay, the theoretical maximum density, okay, which is the gamma t, okay. So now you can check the equation, okay. The first equation we have for calculating gamma t, okay. So in this equation, we need to know PB, okay, which is equal to 6.5, okay. We should also know GSB, okay, and also GB, and also PB here, okay. So just check the equation, okay, provided, okay, for you to calculate gamma t, okay. You will be able to get all the necessary information, okay. And then if you do the calculation, you can get the gamma t is equal to 2.366, okay. Because it's density, so we give it unit, okay, which is gram per cubic centimeter. If it's a special gravity, then we do not need a unit, okay. So that's the difference between density and the special gravity, okay. And then, since we already know gamma t, okay, we also know gamma, okay. Gamma is bulk density, okay, 2.322. But the gamma actually has a unit, okay. Density has unit, special gravity has no unit, okay. But these two, their values are same, okay. Then for calculating voids, okay, L voids, okay, we know it should be equal to gamma t minus gamma divided by gamma t, right, times 100%, okay. Then we can just plug all the values into this equation, okay. So here you can also see that gamma t is always larger than gamma, okay, because the gamma t is the theoretical maximum density. It's the density when we assume there's no zero, okay. So whenever there's any when there's no L void, okay, whenever there's any L void, then its density will definitely become smaller, okay. This is why bulk density is always smaller than the theoretical maximum density, okay. And then we can get the value of L void content, okay. So next we are asked to calculate VMA, okay. So then you can further check what's the equation for calculating VMA, okay. So then you can plug all the necessary value, okay. So in this equation, actually we need the bulk density here, 2322, okay. We also need the special gravity of the aggregate, okay, times 100 minus the binder content, okay. So you can check your slides, okay, the equation, okay, then you will be able to get the values, okay, input for each variable, okay. And for this case, the VMA is equal to 16.5%, okay. So which means, okay, the total volume, okay, the total volume between every particles, okay, is 16.5%, okay, while the total airward volume is only 1.86%, okay, which means majority of the void between particles are filled with the binder, right? Because for the air void, it only fills 1.86%, okay, of total volume, okay. But if you calculate the total volume between every particles, it's 16.5%, okay, which is much larger, okay. That means the remaining part, okay, remaining part of the void is filled with the binder, okay. So which is this one, okay, VFB, okay, void filled with bitumen or void with binder, okay. So void filled with binder can be calculated by using these two, okay. So total volume is 16.5, while for the void it is only 1.86. The remaining will be the binder, okay. So the binder volume then divided by the total volume between particles, then we'll get 88.7%, okay. So this is the solution, okay, for this example, okay. It's quite straightforward. If in the exam, if needed, the equations will be provided, okay. But the meaning of the variables in each equation will not be provided, okay. So you will only have the equation, okay. You should be able to figure out, okay, which variable, okay, which value should be assigned to which variable, okay. Okay, so this is just an example for using the equations.